Hi, I'm Grant and welcome to the study session for radio navigation. Today I'm just going to be answering some questions using a question bank. That way, hopefully we will have a little bit of revision of topics that have been covered so far in the previous classes, and maybe you'll also get a few tips and tricks to help you out with any questions that you might be struggling with during your own practice. But how am I going to get on in the exam? Let's find out. Okay, welcome to this study session. We've done basically maybe two-thirds of the stuff in radio navigation. We've basically done everything that covers ground-based and aircraft-based stuff. The next stuff to talk about is satellites and GPS and all that stuff that's out in space. So for now, we're just going to do a little study session using the airhead ATPL question bank. Link down in the description below for a little discount. Helps me out, helps the question bank out, which is quite a good question bank, must be said. Got a lot of features that you don't get in other question banks. You've got user comments, you've got all the question banks there. You can create your own collections of questions, which is what actually I have done today. I've made a little 25 question selection. I basically started an exam with all the questions in it and just scrolled through, picked out some for each topic. Like this one, for instance, I saw it said primary radar, so I thought, right, I'll add that to collection. I've not actually answered them all. I've just clicked on the ones that talk about relative things to what we've been learning about, and hopefully there's a good variety of questions covering all the subjects. And yeah, we're just going to answer them. Probably going to make some mistakes, but that's the point in a study session. You make the mistakes and you learn from it. So if you've watched anything like this before, it's the usual setup. I've got the questions and I've got my phone linked to the computer just to put some rough notes down, should we need them, for anything, if we need to draw the effing picture, for example. So without further ado, let's get going. So question 1, in a primary radar using pulse technique, pulse recurrence frequency / pulse recurrence rate determines the minimum range, that's the pulse length. You don't want a full pulse still being sent out when the replies come back. The maximum theoretical range, that's determined by the pulse recurrence frequency, because you want to have the pulses coming back before the next ones are sent out, so you know how far away something is. Target discrimination, you can't really do that with primary radar. That's more secondary radar. And beam width is nothing to do with pulse recurrence frequency, so it's going to be maximum theoretical range. Good start. So if we look at the explanation, we can see something. Or, yeah, that's it in more of its basic mathematical format. Max theoretical range equals the speed of light over 2 times the PRF. Yeah, that's basically what I was talking about. Has to go there and come back. Next question. To double the effective range of primary radar, the power output must be increased by a factor of. Right, so this might be worth doing a little bit on the phone. So remember that if we have the signal being sent out, it spreads out. So the power at A compared to the power at B, the power at B is reduced by a factor of the range squared. So the power at B divided by the range squared equals the power at A. So if we want to double the range, we need to multiply the power at B is going to be, 2 squared less powerful than the power at A. So the power at B is a quarter of the strength. So in order to get it to the same strength as it is at power A, we would need to multiply it by 4. But remember, we want it to come back again, so we need to do that again. So it's 4 times 4, so it's going to be 16. Correct. On final, on an ILS approach, you're flying overhead the outer marker you expect to be at. So it's outer, middle, inner, 4, then 1, then 0.3 from memory. So 4 nautical miles is the outer. So look at the explanation. We've got the outer marker, which is 4 to 5 nautical miles. We've got the middle, which is 0.5 nautical miles. And yeah, of course, the inner marker is the threshold. Yeah, this is something you don't really see that much of anymore. You don't see that many outer, middle, and inner beacons. So it's maybe a bit out of date, this information, because most places have a DME. But yeah, 4, 0.5, and then the threshold itself. The captain of an aircraft flying up at flight level 100 wishes to obtain weather information at the destination airfield, which is at 0 feet, from the airfield's VOR, assuming ISA conditions. What is the approximate maximum theoretical range at which he or she can be expected to obtain this information? Okay, so remember the max theoretical range equation for this. That's what we're thinking about here. So if I just get my phone up quickly, we've got the formula, which is the distance that it's, the distance equals 1.23 times the square root of the transmitter plus the square root of the receiver. So then we just plug in some numbers, nice and easy. So we're looking at the distance. That's good, we don't have to do any rearranging, times 1.23 times the square root of the transmitter plus the square root of the receiver. Transmitter is going to be 0, so we just have to think about the square root of the transceiver, which is flight level 100, assuming icing conditions. So we're looking at 10,000 feet. So you're looking at 123 nautical miles. Remember, all these heights are in feet for this equation to work. So 123 nautical miles. Which of the following is a VOR DME frequency that a pilot will tune? So it's going to be in megahertz, that's fine. The range of VORs is 108 to 11795, so it's going to be not this one. It's not going to be number 3. And the VORs are, what's the other thing? It's the evens, or the evens plus 5. So I'm trying to remember in my head now if the ILSs are the even ones or the VORs are the even ones. And I'm thinking that the ILSs are odd. So I'm going to go 108.2. Yes, let's have a look. Oh wow, a lot of stuff. Yes, okay. VOR operates in this range, that's what I said. But then we've got even decimals and even decimals plus 0.05. Okay, there we go. DME measurement is initiated by the interrogator in the DME station, the interrogator in the aircraft, the transponder in the DME station, the transponder in the aircraft. DME measurement is initiated by, so this is the interrogator in the aircraft. Yes. DMA operates by sending pairs of pulses from an aircraft interrogator to a ground transponder. The ground transponder sends a pattern of pulse pairs back to the aircraft, and the aircraft DME equipment calculates range on the basis of the time delay between the transmission and the reception. That's a lovely little summary of how a DME works right there. That's brilliant. Okay, the airborne weather radar uses circular polarization in order to reduce echoes for heavy showers. No, it doesn't mention anything about circular polarization. The airborne weather radar may receive no reflections from a thunderstorm in an area behind a heavy rain shower. That is true because it might get the shadowing effect from a heavy rain shower. The airborne weather radar has a second transmitter working on a lower frequency in order to penetrate rain showers. Not sure about that. And the airborne weather radar has the possibility to detect clear air turbulence behind a thunderstorm by measuring the phase difference caused by the Doppler effect. It won't be able to detect clear air turbulence. It needs something to detect, which is raindrops. So I'm going to go for that second answer there. Yeah, so it's this bit at the bottom that I was talking about. In the area where the shadowing occurs, conditions are unknown. That's what we're talking about. So a microwave landing system not equipped with precision DME, so you're unable to do curved approaches. That's basically what we want. So it provides the capability for not equipped, provides the capability for curved approaches. No. It does provide the capability for segmented approaches, but not curved approaches. Provides the capability for Cat 3 approaches. Provides basically the same approach capabilities as ILS. So it's not curved approaches. Provides basically the same approach. Because it's for segmented approaches. Okay, cool, that's fair enough. Can only provide the same approach capabilities as an ILS. Again, microwave landing systems, I don't know why they're still in the syllabus, but got to play the game, I'm afraid. A vertically mounted dipole antenna is used for RF radio frequency transmissions. The receiving antenna has to be in the same vertical alignment in order to receive the electrical field of the RF transmission in the horizontal plane. No, so it should be in the vertical plane. In the same vertical alignment in order to receive the electrical field of the RF transmission in the same vertical plane. Should be that one, yes. So your, what's it called? Polarization has to be the same. That's basically what this question is getting at. What causes mountain effect and what type of navigation aid does it affect? So mountain effect causes stuff to happen to NDBs because they're a low enough frequency and it's diffracting. Yes. Oh god, there's a big one. So NDBs produce LF and MF radio waves, which primarily travel as surface waves. Surface waves travel over water much faster, so that's not talking about this. The waves get scattered slightly as it crests each mountain and tries to go other side. Yeah, diffraction has an effect on NDBs. What causes coastal refraction? So this is when parts of the wave travel slower and the other parts travel faster, and sort of one bit catches up with the other, causes it to bend or change direction. So the reflection, no, it's not to do with reflection. The difference in height between an NDB antenna and aircraft, nope. The change of the direction of polarization when the surface wave crosses the coastline at an actual angle, at an acute angle. The difference in speed of the electromagnetic wave over land and over sea. There we go. How can a DME interrogator distinguish between its own reply pulse pairs and the reply pulse pairs of aircraft in the area using the DME station? So each aircraft has a unique pulse pair. So the time interval between both pulses of consecutive pairs transmitted by the interrogator wave for each interrogator varies. Wait, I need to read that again. The time interval between both pulses of consecutive pulse pairs transmitted by the interrogator varies for each interrogator in a unique pattern. That sounds like it's good. The DME transponder uses a slightly different random varying delay for each interrogating aircraft. No, because then how would the aircraft know which one is specific to it? On the Y channel, the time interval between the pulses of an interrogator pulse pair is 36 microseconds and or milliseconds, and of a transponder pulse pair 30 milliseconds. The pulse repetition frequency of the pulse pairs transmitted by the interrogator varies for each interrogator in a unique rhythm. I think it's the first one, but the fourth one sounds good as well. The fourth one, there we go. So what is the difference in those two statements really? The time interval between both pulses of consecutive pulse pairs varies for each interrogator in a unique pattern. The pulse repetition frequency of the pulse pairs. So it's the gap in between. That's what the first one's getting at. The first phrase is saying that this bit in here, in between these two pulses, this varies. Whereas the other bit is saying the amount of these come out per second varies. And it's kind of pretty similar thing, but The spacing of each pair of pulses, each pair of pulse pairs, Jesus, it's like a tongue tire, this thing, is different between each group and is random and unique to each transmission. This is known as a jittered pattern. The aircraft DME equipment remembers the spacing of the transmitted pulse pairs and will only accept pulse pairs returned at the same jittered pattern. Okay. So it's, right, so because it sends it out in pairs like that, it's this that is unique. It's the gap in between these, not the gap that's in between the next pair. Yes, okay, that's fine. What describes polarization? So polarization is the orientation of the plane of oscillation of the electrical component of the electromagnetic wave. That sounds good. Orientation of the antenna to the North Pole. Nah, nothing to do with the poles. This is radio nav, not GNav. Rotation of the antenna around a fixed axis. Nah. Orientation of the plane of oscillation of the magnetic. No, so it's the electric component. There we go. A radar which employs an interrogator transponder principle is secondary surveillance radar. Let's look at the others. Primary, no, that's reflection. Doppler, that's reflection. Continuous wave, we don't really look at that. So surveillance radar. Well, we will look at that later, but when a VOR frequency is tuned in an aircraft receiver, the receiver also tunes a DME on if there's any paired UHF frequencies. If there's no paired UHF frequency, it doesn't get tuned. The ILS receiver of an aircraft flying on the ILS centerline will receive no modulated signal because the left and the right lobes cancel each other out along the centerline. The maximum amplitude of difference between the 90 and 150 Hz amplitudes. The same frequency modulated signal from both lobes with the maximum of magnitude. The 90 and 50 Hz lobes at equal depth of modulation. So it's, remember how an ILS works, you've got these two lobes that come out, you've got one that's 50 and one that's 90, and they actually overlap. They don't look like that at all. They overlap, and the center line sort of runs through the middle like that. So when you are on the center line flying down like this, you get the same depth of modulation from each. Nice and easy. Concerning the weather radar display shown in the annex, what is the most appropriate route for the pilot to follow in order to avoid severe weather? The current track is directly through the center of the annex. Okay, so let's have a look. Which one's the best? So we don't want to go A, that's going to be the most severe weather. Let's see if there's any more information. B, again, we're going through some weather at this yellow part, and we don't know exactly what's behind part A. That could be shadowed. C, we know it's a clear path until reaching this part, so I would say C maybe, or maybe the current track. Current track looks okay, but there's nowhere to go if there is bad weather here, whereas with C at least we know there's another way around, so I would say C. Continue on the current track, performing only minor deviations. From the present position, deviate left towards B, then rejoin the track. No. After clearing A, deviate left towards B, divert right towards C, and then rejoin the track. Continue on the current track. Yeah, okay. Fair enough. Bit of both. This is tricky. This is tricky. Okay, fair enough. That's a bit of a subjective one. A Category 1 instrument landing system ground installation provides accurate guidance from coverage limit down to, so this is the categories, you've got Cat 1, Cat 2, 3A, B and C. Cat 1 is 550 meters and 200 feet above the runway. Boom. Next one down, Category 2, 50 feet above, and 3 can give you all the way to runway elevation. The annex includes a navigation display with a VOR tuned and identified on both VOR 1 and VOR 2. What is the radial from the CLT VOR that we are currently on, or do we have selected? What is the radio that we're currently on? So we are currently on, we look at the arrow, is pointing towards maybe 9, 100, 110, 904, 904, 93 or 94, let's call it 94, and we are how many, this is, so maximum deviation on a VOR is 10 degrees, so that means that that's just under 10 degrees to the right of us. So we're going to be 10 degrees further round. It's going to be about, let's call it 94, let's call it 84 would be the current course that we're on, which means we're on the radial. You know what you need to do with this sometimes? You need to draw the effing picture. So we are wanting to be on this one, which is going to be, we're calling it 94 degrees. That's a 4. We're 10 degrees off track, so we are sort of further down here, which means that in order to pick it up, we need to fly to the right, which is what our course deviation indicator, our course deviation bar, is telling us. Oh, the course is selected 093. There you go, it actually tells us at the top. 093 degrees. We're 10 degrees to the left, which means we're going to be 10 degrees over here. We're still flying to it. So if we were on a radial, we're actually going to be further that way. If that's 273 degrees, 10 degrees, that's going to be 263 degrees, because obviously north is down this way. We're looking at it from a weird angle. So I'm going to go for 263 if that's an option. It's not an option, damn. Okay, let's have another look. So these things are quite hard to visualize sometimes. So that cross is the course deviation. We're currently, so we are on the tail of this one, which is 2. Okay, yeah, look at these symbols here. These are our VOR needles. They're both pointing towards the course they want to go. We're 10 or more degrees off. So it looks like we're on 29293, 292. Okay. There's actually a cool app that I was sent called VOR, or told about, that's called VOR Tracker. And what you can do is you can practice these sort of interceptions, and it really helps to visualize if you're unfamiliar with this thing, if you've not done something like this. So you can just click on interception and it'll give you some details. You're intercepting radial 035 inbound. There's tutorials going. Unfreeze it. Let's skip that tutorial. So you can fly around. Our challenge is to intercept radial 035 inbound. If you go to the menu, there's various settings and things you can adjust, like wind. It's definitely worth checking out if you're unfamiliar with this sort of thing. Save those settings, continue the mission. You click on the map there, you can see where we are. So we're obviously very far off. We're gonna have to turn left to go up here, and all you do is basically click the left turn. You can see your aircraft starting to bank. You can see our heading start to change. Good tool to figure out what's going on. If you're struggling for this kind of thing, struggling to visualize, especially with these questions, it can be quite tricky to figure out. So then I could straighten up. And if I look at the map, you can see I'm sort of starting to fly in the right direction. If we were to, I'm pretty sure there's a fast mode we can do. Worth an explore, worth a play, if you're a bit stuck on what to do with these sort of questions. Helps you visualize it for sure. So the next question, an annex includes a navigation display with one ADF and one VOR tuned and identified. What is the QDM to the ARD NDB? So we need to ignore the VOR stuff. So VOR2, this fat arrow, we want to ignore that. we want to go on to the thin arrow, this ARD. And the question was, what is the QDM? So the direction magnetic to the ARD. So if it's going to be this sort of direction, we'll go in 15, 16, 172, I would say. 172. Again, using that VOR tuner app, VOR tracker app, worth a shot. Have a little explore. A primary radar can provide bearing and range, and they are not acquired simultaneously. Bearing and range are acquired simultaneously. Bearing only, range only. They are acquired simultaneously. Yes. Pulse comes back depending on which direction the radar dish is pointed. That's the bearing, and the range is how long it takes to come back, divided by the speed of light. A microwave landing system can minimize multipath errors because, so this is things like reflections off mountains, things like that, and basically it can be interrupted, switched off and on in time to dodge these mountains and things like that. So the transmission can be interrupted to avoid reflection by stationary objects. MLS has a larger beam width than ILS. The transmission reverts to a circular polarization when the beam is reflected by stationary objects. The frequency of MLS is much higher than the frequency, so they can be switched off and on, interrupted. Of the approach aids listed below, which option correctly identifies those that use the VHF band? So a localizer is VHF. That's the same sort of thing as a VOR. So that's 2's definitely in it. So we're eliminating option 3. Locator is normally an NDB. So I'm going to eliminate that. The outer marker. So the frequency of the marker beacons is, was it 75 megahertz? But the actual audio tone is different. So 2, it's actually, yeah, so 75 is within the 30 to 300 megahertz range of VHF. So outer marker and localizer 2 and 3, but the glide path is higher frequency. Outer marker, yeah, is V8 is 75 megahertz. Don't get confused with the sound, the audio modulation that's put on top of it. It's actually a signal sent out at 75 megahertz with modulation in it of a tone that is however many megahertz it is. I can't remember, but it's low, medium, then high as you approach the runway. Almost there then, 24 out of 25. What is the principle behind the predictive wind shear warning capability of an airborne weather radar? So this is Doppler shift in precipitation. So the Doppler shift of detectable precipitation is measured. It's basically exactly what I just said. The change in intensity of a detectable precipitation is measured. The Doppler shift of particles of dust, sand and soot is measured. No, you would need an extremely short wavelength for that. Would be, yeah, it wouldn't go very far. An aircraft's ground speed is measured in the map mode. No, so it's the first one. Last question then. A DME ground station can generally respond to a maximum of 100 aircraft. What is the reason for this limitation? Saturation of the DME ground station working on only one receive frequency and one transmit frequency. Sounds reasonable. The difference in strength of the received signals cannot be differentiated by the DME ground station, and consequently the weakest signals fall off. Limitation of transmission by the echo protection circuit, which avoids replies being reflected and coming back into the DME ground station. Saturation of the DME receivers in the aircraft receiving all interrogations of all other aircraft in the vicinity that are on the same frequency. That's not it. Echo protection circuits, that doesn't sound right. Saturation of the, so I'm thinking 1 or 2. Saturation of the DME ground station working on only one receive frequency and one transmit frequency. The difference in strengths of received signals cannot be differentiated by the DME station, but it can be differentiated by the DME ground station, so the weakest signals do fall off. So I'm going to go 1, because if it cannot differentiate the strength of signals, how can it then drop the weakest signals. Watch that be wrong now. No. So the wording of that question, that answer, sorry, catches it out. The difference in strengths of their signals cannot be differentiated. They can't tell which ones are strong or not, so therefore it gets rid of the weakest ones. That contradicts itself. There you go, there's an explanation. Basically, there's too many signals for it to track, so it limits itself to 100. So if we finish, that's 88%, that's pretty good. I'm answering them pretty fast. Actually, 1 minute per question. It's not that fast. It's probably something like that you need to do in the exam. We got 3 wrong. Let's have a look at which ones we got wrong, see what we need to study. So yeah, this was, again, reading the question, reading the answer correctly, provides the capability for segmented approaches but not curved approaches. So it can do segmented approaches but not curved if there's no DMEP. What other ones do we have? Question 12. So this, yeah, it's the unique signature of the pulse pairs and the little gap in between them, not the gap in between that pulse pair and the next pulse pair. That's what that question's meaning. Oh, not that one. And 17 was, yeah, this sort of quite subjective one. The clearest path, I suppose, is A, but then you reach this yellow bit and you've got a yellow bit here. You could maybe turn into here, then around. I would personally go C and then around to the side like that. It depends where your routing's going as well. If your airport is over here underneath the M, then you might go C and then straight rather than go the long way around. But yeah, all very subjective. Even the explanation said it was tricky. So let's go finish that test again. That's us. Study session over. Hope you learned something. It's worth just bashing out these sort of things. Go through the topics, get familiar with how a question's asked and take your time with it. Read the questions, read the answers. You can do a lot of investigating of the answers like I did in that last one where the answer doesn't actually make sense, it contradicts itself, and you can always draw the picture or draw the effing picture. Sorry, I should stick to my brand. And yeah, you'll be fine. Practice and check out that VR tracker app if you're finding those things a bit confusing. It can be quite baffling if you're not used to it, and it's only really when you start your instrument rating and get familiar with things that you really start to get a hold of these sorts of questions and figuring yourself out in 3D space. That's us. Next class we'll be start getting into the satellite navigation, GPS sort of thing, as well as performance-based navigation, which should take us nicely to the end of the course.